Hello everyone. I welcome all of you on this massive open online course, and today I will cover the topic metasomatism and metamorphic differentiation. Metasomatism: when a metamorphic rock undergoes significant changes in the chemical composition during recrystallization, the process of change is referred to as metasomatism. This can be brought about by the chemical active fluids, mainly S2O and CO2, which add or subtract materials during recrystallization of the rocks in the solid state. Demonstration of metasomatic active depends on chemical evidence in that the original rock differed in composition from the final products. Experience has been shown that the metasomatism actually takes place without change of total volume. This is highly significant in that metasomatic reactions are not quantitatively represented by the conventionally simple equations, which balance equal weight of materials on the reactant and product sides without taking volume changes into account. In metasomatic processes, the principal chemically active fluids or volatiles constituents are S2O and CO2. These hot gases and solution can carry ions in solution and affect mineral transformation along their paths. In extreme case, metasomatism can completely change the composition of a rock. For example, in the conversion of limestone into magmatic ore bodies at contact of igneous intrusions. Goldsmith and Ascola recognize 5 principal types of metasomatism. First, alkali metasomatism. Second, lime metasomatism. Third, serpentinization. Fourth, iron magnesium silica metasomatism. And fifth, metasomatism with introduction of boron, fluorine, chlorine, etc. Now take up alkali metasomatism. This is frequently observed during metamorphism. When alkali migration occurs, this results into replacement of microcline by albite, forming thereby myrmekite at the border between plesioclase and potash feldspar. Second, new information of albite and potash feldspar. It is by this process that many metamorphic rocks like peltic schist were assumed to have been converted into granite looking rocks. This process is called metasomatic granitization. Many batholiths size granite rocks were attributed to metasomatism, in which significant amount of sodium, potassium and silica and S2O were introduced into solid rocks, removing other as basic fonts or concentration as a complementary change. It is for this reason that many granitic rocks show some passive contacts with metapelites. On the other hand, many china clays deposits are the result of the metasomatic alteration of granite. In this process, the feldspar is altered into kaolin. Potash feldspar plus water give rise to Al2SiO5 OH2 plus K2O plus 4SiO2 by what is called sericitization and kaolinitization. Many authors like Carmichael in 1971 consider the alteration of andalusite Al2SiO5 into muscovite by potash metasomatism. By the same mechanism, the crystallization of microcline or albite is contemplated at the expenses of other phase by potash and sodium metasomatism. It is indeed a pertinent question as to how great distance such as alkali migration could be effective. Experiments of Black-Brown in 1968 showed that migration of ions in the solid state is of the order of few millimeter only. Lime metasomatism. At temperature corresponding to green schist phases, certain calcareous rocks may form calcilicate minerals such as diopside, gracilorite, idocrase and scapolite, which form at contact of marbles and granitic intrusive bodies. These rocks of the contacts are called scron, scant terms of West. When a granite intruded a limestone rocks, the contact act as a site of high mobility of fluids that have two origins, one associated with the intrusion and the other fluids liberated from dehydration and decarbonation reaction in the wall rocks. The granite fluids dissolved Si of the granite, while CO2 rich fluids from the country rocks dissolved calcium and other elements. These high temperature fluids develops chemical potential between these two environments, igneous metasediments, and diffuse Si towards the limestone and calcium and other elements towards the granite. The dissolved elements are transported along grain boundaries and get precipitated at a certain distance from the contact, which is a zone of low energy. This mutual diffusion of Si towards the limestone and calcium and other elements towards the granite developed calcite, quartz, wollastonite, etc. Furthermore, since the granite contains a notable amount of alumina, Fe, Mg, potassium, sodium, we get at the contact a varied mineral assemblages of hematite, gracilorite, Vishwavidyalaya, Heidelbergite, etc. The convective fluids may also dissolve other elements successively and precipitated them. This is how tungsten in the form of silicate CaWO4 have formed. Some of the best described example of the lime metasomatism and those accompanying ore deposit of Sudan. Here, the ore bodies consisting of hematite or magnetite with quartz and sulfide ores is bordered by reaction scorn of magnetite, diopside, andradite, tremolite formed by the reaction of the dolomite and the intrusive granite bodies. Similarly, Magnuson in 1966 assumed that parent material to have been sedimentary iron ores along with limestone and dolomites that were altered by regional metamorphism. Serpentinization. During serpentinization, it is akin to S2O Metasomatism. The Mg silicate serpentine form from other Mg bearing silicates such as pyroxene and olivine, whereby Fe is removed along with some Mg by such reaction as Mg2SiO4 phosphorite plus 4 S2O give rise to Mg3Si2O5 OH4, that is serpentine plus 4 MgO. But serpentinization probably can be result from the reaction of aqueous residual solution proceed by cooling of olivine rich pedotites magma, that is autometamorphism. FeMg silicate metasomatism. During FeMg silicate metasomatism, the classic example of FeMg silica metasomatism in silicate rocks and quartzite is in the Precambrians of Finland and Sweden. Askola in 1914 proposed that in the Oslo district of Finland, MgFeSi from the granitoids get introduced into adjoining limestone and formed tremolite, Hedenbergites, hornblende and andesite. When MgFeSi introduced into the quartzite feldspathic leptitite, the result was the production of cordierite anthophyllite gneisses with complementary removal of calcium and sodium. Metasomatism with introduction of boron, fluorine, chlorine and CO2. The result of the introduction of these elements are boron introduction from borosilicates and formation of tourmaline, etc. Fluorine introduction from Grayson rocks, quartz, muscovite, topaz rock form. Chlorine and CO2 introduction leads to scapolite formation, etc. The reader is advised to look into these evidences in field as well as in thin section of rock bearing investigated. Metamorphic differentiation. The term metamorphic differentiation was introduced by Stilwell in 1918 to cover collectively the various processes by which contrasted mineral assemblages developed from an initially uniform parent rocks in solid state. During metasomatism, metamorphic differentiation is generally regarded as a result of differential migration of ions or atoms of metamorphic system through short distance under the influence of local gradients in the chemical potential. These gradients in the rocks are created by 5 main factors. First, differences in temperature. Second, differences in pressure or non-hydrostatic stress as between rocks and open fissures. Third, differences in the chemical composition of the minerals. And fourth, differences in the size of the minerals. And fifth, differences in the surroundings millions. During metamorphic differentiation, every chemical species in a rock will try to reach a place where it actively in low potential. This fundamental law has been especially emphasized by Ramberg as follows: dispersion of minerals at places where the activities are great, migration of the dispersed atoms towards places where the activity is less, and consolidation there constitutes the fundamental process in metasomatism and metamorphic differentiation. The mechanism of migration of different chemical species, ions, atoms or molecules is highly debatable. They are, however, generally considered to disperse or diffuse in the intergranular film through crystal lattice mosaic features. It should be borne in mind that a metamorphic differentiation does not include differentiation by flowing liquids or bodily movement of solid particles. Whatever may be the disperse phase through which ions or atoms diffuse, Ascola in 1932 drew attention to the petrogenetic importance of metamorphic differentiation and discussed in detail the chemical principle involved under 4 headings: concretion principle, secretion, enrichment in most suitable constituents, and solution principle. Concretion principle. The principle explains the growth of large porphyroblasts and crystalline aggregates of certain minerals, garnet, feldspar, cordierite, etc., developed in a variety of metamorphic rocks. From the occurrences of a small crystalloblast of magniferous garnet serpentine with 25 weight% MnO in a low-grade schist of New Zealand, which contain an amount of MnO equivalent to that present in a sphere of schist of about 1.4 millimeter radius. Turner in 1948 computed that diffusion of Mn occurred through a distance of 1 to 2 millimeter. Concretion may have different composition. For example, quartz concretion in low-grade peltic schist, calcareous concretion in marls and low-grade impure sediments. Certain concretion also contain quartz plus feldspar, and as such, the concretion pegmatites as small bodies with biotite slaves are found in niches. Secretion principle. The growth mechanism in this process is opposite to the growth of concretion that proceed from the center of the spheroids outside. Cavities, open cracks, or fissures in the rocks are found by shear and tears. This result into the mechanical pressure gradients, which in turn creates corresponding gradients in the chemical activities of the rock constituents. The mobile constituents will migrate towards the low pressure zone, for example, cracks or fissures, and then consolidates in a new minerals. This process may account for some pegmatites which have zonal structures, as in southern Norway described by Anderson in 1932, where the pegmatites are so to say ductile bodies. Reeder in 1934 and Chapman in 1952 regarded quartz veins in metamorphic rocks as product of secretion. In figure, the origin of quartz vein in quartz kyanite stolite mica schist is explained. The immediate contact of the veins with the country rock is a concentration of kyanite and stolites and development of quartz vein. This suggests that quartz have migrated from the zone, leach zone, adjoining the cracks new occupied by quartz vein. Chemical analysis of the rocks from veins, contact zones, and the country rocks shows an enrichment of Al2O3 and more improvisation of SiO2. The leach out zone with concentration of kyanite and stolite is almost devoid of quartz, since SiO2 migrated towards these cracks. Principle of enrichment in the most suitable constituents. During progressive metamorphism, or if two chemically incompatible rocks are brought together in contact, various minerals will become stable. A good examples can be cited from veinite or vein niches migmatites which quartz feldspar have separated out from original metamorphic schist. As a result, the residue becomes rich in FeMg minerals like cordierite, biotite, garnet, and iron oxide with or without sillimanite. The development of biotite at the contact of muscovite schist and amphibolite is also an example of the enrichment in most suitable constituents. In skarn rocks, the effect of local or zonal enrichment in most stable constituent is frequently seen for geochemical migration and metasomatic exchange in rocks. The principle of enrichment in the most suitable constituent is of great importance. This process often operates in combination with solution principle. Enrichment of garnet around a folded inclusion of limestone in granite is an example shown in figure is taken from birth in 1962. The garnet still represent an enormous concentration of iron. Solution principle. According to this principle, the most soluble, that is most unstable minerals or mineral association are dissolved and move away to environments in which they are stable. Large rock masses are changed chemically by the removal of certain soluble constituents. For example, all basic igneous rocks and also amphibolites of similar composition commonly loses calcium oxide if they recrystallize in a low temperature phases. In oceanic basalt, plagioclase altered to albite and epidote, forming spelite. Similarly, amphibolite hornblende plagioclase rocks changes into a low temperature green schist. In the same manner, the expulsion of CO2 during metamorphism of impure dolomitic limestone may be regarded as a removal of the most soluble components. This CO2 at other places may become less mobile under different physicochemical conditions and crystallize as calcite porphyroblast and calcite quartz vein in certain low-grade schist. Thank you very much.